A particle of mass m is shot with an initial velocity vi, making an angle theta with the horizontal, as shown in figure P11.17, right here. The particle moves in the gravitational field of the Earth. Find the angular momentum of the particle about the origin when the particle is A at the origin, B at the highest point of its trajectory, and C just before it hits the ground. D, what torque causes its angular momentum to change? So I drew another diagram here, and it wants us to find the angular momentum about the origin at several points. So part A, what's the angular momentum about the origin at the origin? So if we think about that, just logically, the particle is at 0, 0, right, in terms of an r vector. And there is no velocity here. There's velocity right after, but if we just use L equals I omega, we should get 0 kilograms times meters squared per second, right? I would think so. So in that case, in that case, the angular momentum is 0 at the origin. Part B wants us to find the angular momentum at this point where the trajectory is at its highest y value. So what we do know is that the velocity at this point is the exact same. In the x direction, the velocity at this point is the exact same at this point, as it is at this point, as it is at this point, because we know that in the x direction, the velocity remains constant all the way throughout this trajectory. So we know that it's going to be velocity not cosine theta. You know, cosine velocity, velocity not times cosine theta. And why do we need to know that? Well, so we can find the momentum. So the momentum is equal to, mv, we know that. And if we think about it, there's no momentum in the y value if there's no velocity in the y value. So if the velocity is 0 at this point in the y direction, there's no momentum in that direction. However, in the x direction, we do have a velocity for that value. We do have a mass. So mass times velocity 1 is equal to the momentum at this point. And then we should utilize the stuff that we learned, the cross product of r, the r vector, and p. R represents a displacement vector, p represents the momentum vector. Now, r is something, we don't know what it is, but we know that it's traveled in the I direction and in the j direction. So we know it's going to be something I plus something j. Well, if we think about where it is, it's at the highest point. Then it's gonna be at exactly halfway of the total horizontal range of the object that it's going to travel. So at any point, in any scenario, if it's on the gravitational field of Earth, we do know that it's going to be half the horizontal range at the highest point of trajectory. So that's going to be r over 2. We're going to say r is the horizontal range, and that's going to be in the x direction. In the y direction, well, that's a different story. We have to calculate that. So what I did was I used kinematics. And I'm just kind of tilting it here so you can see. We don't know what the change in y is. We're finding that. We know that the final velocity right here, it's 0 meters per second. It's in the y direction, right? And the velocity initial is going to be velocity naught times sine theta, right? And that makes sense because the initial y direction in the initial velocity is velocity naught sine theta, times sine theta. We don't know the time, and we won't need to. And we know the acceleration is negative g in the y direction. So I did some scribbling there because I messed up a few times. But if we use the kinematic velocity final squared equals velocity naught squared plus 2a times change in y, we should be able to find change in y. Velocity naught, right, in the y direction is velocity naught sine theta. And that's equal to, that's what I just said. And then you know that a is negative g, so it's minus 2g, and change in y is the variable we're trying to find. So if we isolate change in y, we should get velocity naught squared times sine squared theta over 2g. Thus, if we now we have a displacement vector. So what was weird scribbles before became half the horizontal range in the I direction, and velocity naught squared times sine squared theta over 2g in the j direction. So now we take the cross product. Angular momentum equals R cross P. Order matters because if we'll put this in front, it would be a different value. And we make our little table. 0 minus mv naught cubed sine squared theta cosine theta over 2g is our angular momentum. So our angular momentum is negative mv naught cubed sine squared theta cosine theta over 2g. Or if you want to be extra fancy, it's negative mv naught cubed sine 2 theta sine theta over 4g, using those trig identities. And what's important is that the angular momentum is in the z direction. So after this, it's in the negative z direction. Going, if we have an x, y here, it's going in the z direction. Negative z direction, excuse me. Part C wants the angular momentum at this point, at the very point it hits the ground. So we're going to use this formula again, L equals R cross P. So this time we know for sure because it's traveled all the way across to the very end point that it's meeting. We do know that it's in the x direction, the displacement vector is r, capital R, which we define as the horizontal range. But it's anywhere in the air, so it's right where it started, at the ground, so there's nothing in the y direction or the j direction. So it's just the displacement vector is just going to be capital R in the I direction. The momentum is a slightly more complicated, slightly more complicated thing to calculate because we have momentum in the y direction because the velocity is going diagonally. We have momentum in the y direction and in the x direction. So we know it's going to be mv2 in the j direction plus mv2 in the y direction, in the I direction. I screwed this up. Okay, j represents the y, and I represents x. So we know that the second velocity at the x direction is equal to the initial velocity of the x direction because we defined earlier that on the gravitational field of Earth, the x direction velocity is the same. It's constant. But the y direction in the y direction it's not constant. So we need to find what that is, and with kinematics we can. So using this kinematic again, we can find time. So we are just going to find when we know change in y is equal to 0 meters. Velocity naught is equal to velocity naught in the y direction, which is equal to velocity naught sine theta. And velocity final we don't know. Time we don't know. Acceleration is negative g because it's in the y direction. So once we plug these values in here, we should be able to factor out t and find out what t is. And t is equal to 2 times v naught in the y direction over g. Then we're able to plug it into another kinematic. Velocity final is equal to velocity naught y, minus g times 2 times v naught in the y direction over g. So we know that velocity final is equal to the negative velocity initial in the y direction, which is negative velocity naught sine theta. So P is equal to m times those two values that we found. Now we know that velocity naught cosine theta, which was velocity 2x, that's going to be our x part of the vector. And we now know that in the y direction and the j direction, it's negative v naught sine theta, which we just calculated. So now we can finally plug in r cross p, ri, in the I direction, cross velocity naught cosine theta in the I direction, plus negative v naught sine theta in the j direction. And we use our little table here again, and we're able to cross this and see that we get negative r v naught sine theta times 0, or minus 0. So our answer for the angular momentum is negative r v naught sine theta. Finally, we should be able to calculate part D, which is what torque causes its angular momentum to change. So remember, torque is equal to dl dt. Torque is, the very definition of torque is change in angular momentum over change in time. And I drew a little diagram here for us to understand, because if you imagine a ball that's being thrown up like this, okay, it's being thrown, it's going to be rolling like in this direction. If you're exerting a force this way, right, and it's tangent to the ball, the ball is going to turn this way. And I drew that here. So there's a torque in the y. There's a torque that's going this way due to gravity. This is G. So we now know, if we remember the right-hand rule we learned, that if it's going this way, whichever way our thumb is pointing is where the torque, direction of the torque is going. So the torque that's being applied is in the negative z direction. So the torque that it takes to change this is a negative torque, and it's a torque in the negative z direction.